Hi everyone, my name is Elodie Bouzbib. I'm currently working at Tupna Lab in Pamplona, Spain, and today I'm presenting Haptixel, encoding data through cutaneous force-based and counter-type fingertip haptics. Data can be encoded through various sensory channels. For instance, data physicalization has been widely explored as physical artifact whose geometry encode data and has highlighted how physical properties can enrich the interpretation of quantitative information, including both static and dynamic physical representation. Let's say we touch it and directly interact with it. Well, we feel this geometry. Through our skin, we feel the texture, the pressure, the force changes. At the fingertip scale, when we physically interact with tangibles, the fingertip pulp and its skin deform and provides a cutaneous feedback to our brain for interpretation. More importantly, we're used to quantify it through our touch. We map whether a plate is too hot with temperature or if a fruit has passed with its compliance. So now, what if we remove the data physicalization and focus on our sense of touch? Can we encode data through cutaneous force feedback in visualization tasks? In this paper, we're interested in knowing whether cutaneous force can function as a quantitative channel for visualization contexts, treating force as a univariate value mapping to either reinforce and augment visual perception or to provide a lightweight alternative when attention is limited. To answer this question, we propose Haptixel, a wearable haptic device designed as an accessible platform for studying force-based color cues as haptic pixels in visualization tasks. Haptixel's concept is to encounter the user's fingertip to provide this cutaneous force-based haptic feedback. Here, for instance, on the gray pixel, Haptixel is actually not touching the user's fingertip. It then encounters it to provide force depending on the pixel's height and color. The red pixel has a higher force than the yellow one. Hardware-wise, Haptixel's design is open source and really simple. It relies on a servo motor, a crank rod mechanism providing a lever actuation, a finger support, and finally, a proximity sensor, a force sensor, and a vibration motor. When the servo motor is on, the lever deforms the user's fingertip pulp. The design choices from Haptixel open up a three-dimension interaction framework. Similar to visualization tasks, Haptixel can be used without visual support over 2D displays in AR or in VR. We designed Haptixel's form factor to be compact to avoid occlusion while working with typical hand tracking systems. Its second dimension is its force levels. We severed Haptixel in force so we can control the feedback it provides. First, Haptixel can stay out of reach without physical contact. When touching the fingertip, Haptixel can provide a simple contact without force and provide the user with a light touch. Finally, it also provides low to high forces, either touching or pushing on the user's fingertip. The third dimension is the contact type, either a discrete contact, like a stroke, or a continuous one. A continuous constant contact of a given force provides an absolute information, while a continuous varying force indicates more relative information, such as ascending or descending. What are the opportunities for data visualization? Well, dimensions can be combined to cover a whole set of mid to low level visualization tasks, but supporting them goes through both technical and perceptual requirements. Technically, Haptixel requires accuracy and precision when providing feedback to map a wide range of forces, a low latency when changing forces, and a low just noticeable difference, the GND, to multiply the user's discrimination levels. Perceptually, users wearing Haptixel should demonstrate a good force discrimination used in discovery tasks, a high accuracy and absolute recognition, for instance, used in information retrieval, a high accuracy and relative recognition used for sorting or comparing, and a low spread within the same data branch that can be used for correlation tasks. So first thing first, we'll start by evaluating Haptixel's GND as a technical and perceptual key parameter. Haptixel relies on the skin deformation to provide pressure levels and convey forces. So we realized that the material in which Haptixel's finger support is printed would potentially impact the user's perception. For instance, if you press on your fingertip pulp being free of any constraints, it will deform plainly. However, if you constrain it, for instance, with your other hand and you press on it, the pressure perception you receive is drastically different. We therefore decided to quantify the material impact over the user's perception with a flexible material support and a rigid one. To do so, we conducted a psychophysical experiment to quantify Haptixel's just noticeable difference, the GND, using those two printing materials. We recruited 8 participants and used 5 reference stimuli that were perceptually compared to each other. Participants had 0 distractions and answered on the computer using the keyboard and their non-dominant hand. We used a within design. All participants performed the experience with the 2 materials, and we used a Latin square for the order of the conditions. Participants first received a reference stimulus for a second, then the contact would be off, and they received a comparison stimulus. Finally, participants completed the question. The comparison stimulus is higher or equal than the reference stimulus. For instance, let's say that the values were randomly chosen as 0.5 Newton as a reference and 2.5 Newton as a comparison. When users were pressing higher or respectively lower, then the difference between the comparison stimulus and the reference one was divided by 2. This would go on until the participants found the stimuli to be equal. Then the GND would be the last value to be considered as different. Then another tuple of reference and comparison would be compared. We plotted the results here with the PLA, the rigid material, in blue, and the TPU, the flexible material, in red. We see that the GND is better with TPU as it's lower. In Weber fraction, being the ratio between the GND comparison stimulus and the reference one, we see that the ratio is around 0.5. We performed a one-way repeated measures ANOVA, where we saw a significant effect of material on the GND results. These results thus reveal that users should be able to discriminate different levels of forces, and that this discrimination will be more precise using a flexible finger support, probably around 0.6 Newton separation between levels. Using these results, and with respect to our research question, we then conducted a user experiment to demonstrate whether cutaneous force levels can support quantitative distinctions and be retrieved accurately even without visual feedback, substituting visual encoding. We designed a VR pixel art-like application where participants haptically explored physical patterns which they could not visually see. Participants had to replicate them as coarse heat maps on the blank canvas with colors matching the force levels they perceived. Participants felt and drew 4 patterns. The first one only had 1 force level, representing a cross. Here, the participant draws the cross with a yellowish color. To define this color, participants have a calibration cube to refer to. The difference with this cube is that they control its color and are provided with its corresponding force. They can therefore match the force they perceived on the canvas to the calibration cube one. In the second level, we represented triangles with 2 levels of forces separated by 1.5 Newton. In the third level, a random design was to be found to remove the bias of drawing known shapes. It grouped 3 levels of forces separated by 1 Newton. And finally, the last level was circles with each force level separated by 0.6 Newton as per the GND limit. We recruited 16 participants and all of them performed the 4 patterns of 5 to 5 pixel art canvas. We measured the participants' assigned forces. Using the same color heat map, we can see here on the left the pattern to find, and on the right what the participants have drawn in average. Same goes for the second level, the third level, and the fourth one. First, we see that thanks to its uncontoured concept, the on-off, the gray to colors, are really well defined. Regarding global results and considering all the gray cubes, the global absolute error was under 0.2 Newton. And without the gray cubes, it was 0.34 Newton. But now, what I think is interesting, and even though the absolute error is actually pretty low, we can notice that sometimes the colors aren't reached, as here in level 3. Though, each color level is still recognized and well discriminated as belonging to the same sublevel. This does mean that relative forces are understood properly and force levels can be discriminated. We decided to look into the data spread by analyzing the 95 CI per force level per user to show how participants were confident pixels were associated among one sublevel. Results were shown to be between 0.05 Newton and 0.3 Newton. Finally, we performed a one-way repeated measured ANOVA for the last pattern with the 4 force levels. There was a high significant effect between all the sublevels, indicating that participants can discriminate at least 4 force levels using Haptixel plus the non-contact one. We also see that the average and median value are really close to the absolute expected values. Qualitatively, participants mentioned they got lazy to go back to the calibration cube all the time and preferred using pressure and force memory to draw the patterns than to go back to the cube. They mentioned how easy it was to rely on relative force perception to draw the patterns. Strategically, they mentioned using the validation phase to detect if there was a global offset, an under or overestimation, and reiterate from there. Finally, they were all quite surprised by the amount of forces they received on the fingerpad and weren't expecting it. From the study, we highlight 5 key findings and their implication for data visualization tasks. First, participants perceive the difference between no force and force, meaning that participants can freely discover values in visualization tasks, hover void zones, and encounter data points with an associated value. Participants differentiated relative force levels and actually used it as a strategy to retrieve values, meaning that continuous force values can be interpreted as mapping while exploring data. Participants significantly differentiated 4 force levels, which, compared to the literature using vibration or kinesthetic feedback, for instance, demonstrate how Haptixel and more generally cutaneous force feedback are a viable alternative to encode data in visualization contexts. Participants retrieved absolute force with a high accuracy, meaning that Haptixel and cutaneous force feedback can be used when visual attention is limited and to complement visual encoding. Finally, participants clustered data points with a really low deviation of data, which demonstrates how beyond mapping a force value, cutaneous force feedback supports more general visualization tasks such as clustering or correlating. We envision a set of use cases for Haptixel and more generally cutaneous force feedback in visualization contexts. As participants can discover, retrieve, and interpret spatial data, we propose a first use case of geographic data visualization, illustrating how cutaneous forces can convey topography information, forces to heights, or check population density, forces to density. Participants in our study perceived dynamic changes of forces and actually revealed heavily relying on them on the relative force changes. So these results can be extended to temporal exploration using Haptixel, for instance, in stock market trend following. Haptixel can encode dimensions as derivative, for instance, trends, slopes, or speeds. As a conclusion, we presented Haptixel, and our contributions are a lightweight open-source fingertip haptic device designed as an accessible platform for studying cutaneous force-based color cues in visualization, empirical quantification of cutaneous force discrimination thresholds on the fingertip, including the effect of support material on the user's GNTs, and empirical results demonstrating that cutaneous force feedback can support simple quantitative distinctions and encode data, enabling users to reproduce coarse color patterns without visual feedback. You can find more information in the paper, and Haptixel's design and scripts are available on my website. Thank you for your attention.